why not? All right, so moving on to the lecture for today. So this is the third lecture, and the topic of today will be automatic differentiation. So we'll start by reviewing a bit of calculus, if you don't remember what you've seen back in your bachelor. Then we'll have a bigger piece on automatic differentiation, like a few or two algorithms that you can use to implement automatic differentiation. Then we'll dive into a few more details regarding the implementation of these systems in deep learning libraries. And finally, I want to show you a few examples of use cases of automatic differentiations that go beyond neural networks. So maybe this lecture today will be a bit heavy. It might be a bit difficult to follow because it's quite low level, and it's also combining mathematical notations that are not too difficult, but that you will have to ingest in order to properly understand what's going on. And so, with this disclaimer, what I want to say is that, and I will quote Roger Gross that you see in this slide, is that implementing backpropagation by hand is like programming in assembly language. You will probably never do it, but I think, and I share his opinion, it is important for having a mental model of how everything works. And this is really what I want you to get from this lecture. I'm quite certain almost none of you will have to re-implement backpropagation again in the future, but understanding how this algorithm works, I think it's quite important in order to really make sure you understand this philosophy behind deep learning and behind differentiable programming. All right. So the motivation is that, as we have seen last week, it's quite easy to define neural networks. So we have seen a first architecture, which we call the multi-layer perceptron, and which we define as a composition of smaller and simpler units, which we call the logistic regression units. And then what I've told you very quickly is that we obtain this architecture, then it comes with many parameters. And the way we would adjust this parameter is by using gradient descent, and more specifically using a variance of stochastic gradient descent. However, what we need for this algorithm to run is to be able to evaluate the gradient of some loss function with respect to the model parameter. And so when it comes to this kind of models, you could try to derive the gradients by hand, and it's actually what we'll do today. But you will see very quickly it's quite tedious and very error-prone. And so when you have larger and larger models, this is something you definitely don't want to do by hand, but that you would like to automate by an algorithm, right? Also, so in practice, this becomes quickly impractical for complex problems, for complex models, but also, and I think this is a stronger reason, every time we would make changes to the model, then it would also require rederiving the gradient that you would have derived by hand quite laboriously, right? So the family of algorithms that we'll see today together is called automatic differentiation, or AD. And so AD provides basically a family of techniques for evaluating the derivatives of a function when this function is specified by a computer program, right? It's not specified by an equation, it's specified or implemented by a computer program. And what we want is to take automatically the derivative of this computer program. You should understand that this family of techniques is different from symbolic, for example, from symbolic differentiation, in which here the goal is rather to try to start from a mathematical expression, then trying to identify another and human readable expression of the derivative of that expression. Here you will see that the kind of derivation of expression for the derivative that we'll get, they are not quite human readable, even though if you just compute them, so evaluate their value, they will produce the exact value of the derivatives, which is what we are more interested in. And finally, it's also different from numerical differentiation. So in particular, algorithms or techniques like finite differences, in the sense that the algorithm that we see today is exact. It will not introduce, for example, rounding errors as you would have when you use finite differences. Of course, up to the precision of the floating point number. But otherwise, the algorithm is exact. All right. So the first important concept you should try to keep in mind is that a program, when you look at it, like this piece of Python code written in JAX, JAX is a library in Python which you can use to write differentiable programs. It's used, for example, to write neural networks. Well, this program is nothing else, when you look at it, is nothing else than a composition of primitive operations, primitive instructions, so fundamental instructions, which we know how to derive individually. Right? And so if you remember from last week, I quickly mentioned the chain rule. Well, the chain rule is something you can use to derive composition of functions in terms of the derivatives of the individual element of this composition. And so this is exactly the principle that we'll use today, except that the way we'll represent a function is with a computer program as the one shown here in this slide. And indeed, what is done here is, so you have, for example, a first function which corresponds more or less to a multi-layer perceptron. It takes inputs, it takes as arguments some parameters and some input values. And then, assuming, for example, these params is yielding pairs of W and B for the matrix and the offset, then by just looping over this value, so that would mean looping over the layers from the start to the end of the network, what we can compute is the intermediate activation of the layers. So you just take the dot product of the inputs with W plus B, and then you pass these intermediate values through an activation function like the hyperbolic tangent. Last week we've seen other activations like the sigmoid activation and the ReLU, but the hyperbolic tangent is another one. You repeat this, and then at the end you return the value which is returned by the predict function is the output of the final layer. And then you can also define, for example, a loss function which takes as input some which compute the predictions with respect to some input for some value of the parameters, and then you would compare, for example, the quality of this prediction with respect to some target values. And one way, for example, if you are doing a regression, so you want to predict a real value, would be to use the squared error and to look more specifically at the mean squared error, right? So this function would itself return now a scalar value, right? And then this framework, what do they do is that they allow things like, okay, now that I've defined my loss function, I can directly differentiate, so obtain the derivative of this loss with, for example, the first argument, in this case, the parameter. And now this new variable grad fun, so for the gradient, is itself a Python function which you can use to evaluate the derivative of the function at any parameter value. So what we'll try to do today is to understand how this grad function is actually implemented. What's the magic which is happening there for this to work? Because I could have put anything I wanted in these two functions. How does it know how to compute the gradient of the loss, which is arbitrary, and to produce correct values for correct derivatives? And actually, you can do things that are even a bit crazier. So most of the modern frameworks like JAX, but it's the same for PyTorch or TensorFlow, they also allow higher order derivatives. So not only, for example, you could obtain directly the gradient of some function that you define. So for example, if I wanted to redefine for some reason the hyperbolic tangent, I would do it in this way. And then I could use JAX and its grad function to obtain a new function which represents the derivative of this hyperbolic tangent. But another thing that I can do is to take the derivative of this derivative. So I could code grad again on the output of the grad function. So that would compute the second order derivative. And so this now FPP would correspond to a function, a Python function, which I can use at any value of x. And that would give me the second order derivative of the hyperbolic tangent. So we'll see also how does that happen? How is this possible? Even again, I could have put anything in this function. And I could do that, of course, for third, fourth, fifth order if I wanted. All right. So we'll start with a quick recap on calculus. So first, I have to remind you what is the definition of a derivative. So at first, we'll consider a function f, which will take as input a scalar value in R, and will return as output another scalar value in R, right? Then we will say that the derivative of this function f, right, is, and I'm just introducing notations here. I will denote this derivative either as f prime x, and this would correspond to the Lagrange notation, or I will denote it using the Leibniz notation, and this is the one actually I will use over and over today. So, and I will define it in this way, using this partial symbol. And what does that mean? So by definition, we'll say that the derivative of f corresponds to the value of this limit. So what does it represent? So it's the difference between f of x plus h and f of x over h. And so h will correspond to a small offset a small quantity. And so you look at, as you just slightly change the value of x, for example, what's basically the change which is induced on the value of the function, right? Then you take this limit as h tends to 0. So the interpretation of that is that the derivative will correspond to the instantaneous rate of change at x. And so for example, so if you start at x, right, you can evaluate the function that will correspond to f of x, right? And you could do that at any x value. And so this is our function in plain red. And then one thing you could look at is, what if instead of looking at the value of f at x, I looked at it at x plus h, right? So I would look at the value of f at this point, and that would give me this value. And now what you could do is to So if you look at the straight line passing through f of x and f of x plus h, right, you would have this one. And what is interesting there to understand is that the slope of this line is given by the ratio of the values of the function, which I will call delta f, which corresponds to this difference between f of x plus h minus f of x, and the ratio of this delta and the value of h, right? And so what will happen is that as this quantity h gets smaller and smaller, while this line will go to the turn to the left, and eventually when h tends to 0, it will match with the line which corresponds to the tangent here, this one here, to the tangent at f of x, right? And so an interpretation of that is that the slope of the tangent is the derivative of the function and it corresponds to the instantaneous rate of change at x. Right? So that means if I increase my value, so as you increase x by some unit h, what you are looking at is what is the impact on the value of f. All right, so you should be quite familiar with that, or you should have seen that in the past at least a few times, I suppose. All right, so this can be generalized to higher dimensions. So the first generalization is instead of considering a function f, which is going from scalar values to scalar value, is to consider a function f which takes as values vectors, right, and not scalars anymore. So it takes as input some vector in Rn, but then this function is still scalar valued, so the output is still some value in R. And then what we'll do is that we'll define now the gradient of this function as the vector of the partial derivatives of the function with respect to each one of its arguments, right? So this is what we'll denote with this notation. So nabla of f of x will define that as the gradient of the partial derivative of the function with respect to each one of its arguments. So it's as if we were just considering a bunch of derivatives, one for each one of the arguments, and we say that, okay, for example, if we look at x at the first argument, it's as if we were freezing all the others, so x2, x3 to xn, to the values that you pass in x, and then you just look at the derivative of the function with respect to the first one, with respect to the first argument. Right? And you could do that, of course, for all n arguments. Right, so the gradient is a vector that gathers the partial derivatives of the function f. Right? You could also apply the definition of the derivative coordinate twice, and what you would have is that the component j in this vector, right, corresponds to the partial derivative of x with respect to xj, the j's argument, evaluated at x, and that corresponds to the limit, the same as before, except now we have replaced h by h times ej, where ej corresponds to the j's basis vector. Right? So it's a vector full of zeros, except at the element j, which is equal to 1. So, Victor, there is a question, isn't it gradient f a function from Rn to Rn? So no, I'm really defining just first the gradient. So it's a function which takes as input a vector, but returns as output of a scalar value. So this is correct. But, and I think this is maybe your question, of course, we could have defined instead a function which takes as input vectors and also return as output other vectors. And so this is what I will write with this bold notation, bold f, to mean that the value of f is a vector and no longer a scalar, right? So if you do that, you can then generalize further the definition of the gradient, and what you obtain then is called the Jacobian, and that corresponds to a matrix in which you have m times n elements, so you have as many rows as you have outputs for the functions, and you have as many columns as you have inputs. Yes, as you have inputs from 1 to n to the function. And then each entry of this matrix corresponds to the partial derivative. For example, if I take this of at ij, it corresponds to the partial derivative of the I output of the output I with respect to the input j, right? And so you can also express it in this way as a set of columns where you take the partial derivative of the function with respect to each one of the arguments, or also you can view that each row corresponds to the gradient of the function with respect to one output, right? And so in a sense, you can also view the gradients transpose as a Y Jacobian in which m is simply equal to 1. Right? If you look at this, so this quantity, this vector is one row. So if m is equal to 1, that would correspond to this first. All right, so now that we have defined these quantities, what we'll see together is how to compute them when this function f, are defined as computer programs. So the first easy case is to assume that our function f, so taking as input a vector in Rn and then producing as output another vector but in Rm, we'll assume that this function f decomposes as a chain composition. So we just say that we've defined f as a composition of simpler functions, right? Where we have first applied the function f1 to the input x0, that has produced some intermediate quantity x1, and then we put that as input to a second function f2, which produces again another intermediate quantity, and we repeat that for a certain number of times until we've produced the quantity xt minus 1, which we feed to the last element of the composition, ft, and that produces the actual output xt of our function f, right? So we'll say that, so f is defined in this way using this kind of composition, using a composition of elementary functions fk, where each of these fk, and this is a notation that I will reuse, so nk will correspond to the dimension of my variables xk, the one that I produce as output of the function fk, and the dimension of the input of this fk function will be nk minus 1. Well, so a quantity that we'll try to estimate is in particular the Jacobian of xt with respect to x0. Right. This is in the general case what we'll try to derive. And so that Jacobian matrix, we can compute it, or we can express it by using the chain rule. So the chain rule states, in this case, for example, that the Jacobian of xt with respect to x0 is equal to the Jacobian of xt, the last quantity of our chain, with respect to xt minus 1, right, times the Jacobian of xt minus 1 with respect to x0. And what you see here now is a recursive definition. This is again a Jacobian, which we can express recursively using the chain rule. So that means we can expand this expression into a whole bunch of other terms. And then what you obtain is this expression, which says that the Jacobian of xt with respect to x0 can be defined as a product of Jacobians. So the first one being the Jacobian of xt with respect to xt minus 1 times the Jacobian of xt minus 1 with respect to xt minus 2, and so on, until we arrive to the Jacobian of x1 with respect to x0. Right? So all these things, what you should keep in mind is that they represent matrices, right? These matrices here. Except that we don't have f and x, we have x, for example, xk at the numerator and xk minus 1, for example, at the denominator. Okay, so now we have re-expressed our problem of trying to compute this Jacobian as a product of matrices, right? And so we have a bunch of matrices, and so there are several ways we could try to compute this product. And so two ways to do it, but of course there are more, would be to first compute the factor which correspond to the product of the last two factors in the expression. And then, so that would give then another a matrix. And then to multiply this matrix by the one next to it on the left, and to repeat that over and over until we end up with a single matrix, which will then represent this Jacobian. But of course, we could have done this multiplication of factors in other ways. And one special other way is to do exactly the same, but in reverse, in which we would have started with the last. So we would have taken we would have first computed the product of the Jacobian of xt with respect to xt minus 1 times the Jacobian of xt minus 1 with respect to xt minus 2, right? So that would correspond to this first two terms here. And then we will have multiplied this matrix, this resulting matrix, by the one next to it on the right, and so on until we arrive to the end of the expression. And so these two ways of computing these Jacobians, the first one is called forward accumulation. It's called forward because you start with x1, you start with x0, x1, and then you go forward in the direction of the composition, right? So you compute the product in this way by going from the left to the right. And of course, the other one is called reverse accumulation because you start by the end of the chain, right? You start with quantities that correspond to the end, so to the right of the chain, and then you reverse the computation. So you go backwards, you go in reverse to compute the product of these Jacobians. All right. So actually the direction that you pick is quite important because it will set the complexity, the computational complexity of the evaluation. So the first thing we'll do today is that what I'm telling you is that the time complexity of the forward and the reverse accumulations are not the same, right? In the case of the forward accumulation, it's proportional to this expression, and in the case of reverse accumulation, it's proportional to this expression. And then, depending on the values of n0 or nt, one will be better than the other. So let's see why this is the case. I will switch to the iPad to do that. All right. Okay. So what we want to compute is the Jacobian of the output with respect to one of the inputs. So let's say x0. And this is, by the chain rule, equal to Jacobian of xt with respect to the immediately previous intermediate variable, so t minus 1 times, then we do that recursively, xt minus 2, we do that through the chain until we arrive to, for example, x2, x1 times okay, so this is the chain rule. Now you can view that as a product of matrices. So here what we would have is, for example, a matrix that I will denote by AT, which has a number of rows which correspond to NT. So remember, NT is the dimension of the variable xt, and which has a number of columns which is equal to nt minus 1. Right? Similarly, for this guy, now we would have a number of rows which is equal to this one, so at minus 1, and a number of columns which is another quantity, nt minus 2. T minus 1, and sorry, t minus 2, and that would correspond to at minus 1. Right? Then we would have the other ones. Then maybe here what we would have is a 2 and 2 and 1, and then finally the last one, 1, and maybe quite a few columns. And 1 up. Okay. So now I'll just copy this a few times, duplicate. So let's see what would happen first if I compute this product using forward accumulation. So if I do forward accumulation, what I would do is that I would start with a product at the very right. So I would first compute this one. Right? And so when I multiply these two matrices, I have to implement some product operation, and the complexity of this operation, it would be it would be proportional to the, in this case, to n2 times n1 times n0. Right? And the result of this would be a new matrix of size n2 times n0. Okay. Then for the second step, I would have to multiply this resulting matrix with the one here just on its left, right? So now the computation of this product would be, so we would have here now a matrix of size n2 times n0. And so here now the computation for the second product would be n3 times n2 times n0, right? And so we would have to repeat that. We would have the second one, maybe here. No, sorry. Then you do that a few times. Right. Here the computation would be equal to, finally what we would have is the final computation, which would have a complexity of nt times nt minus 1 times n0. Because what could happen is that the number of columns of these matrices that we compute, right, it would always remain equal to n0, because this is the final, this is the dimension of the matrix at the very right. Right? And so now if we add all these computations together to compute the product of all these Jacobians, what we would have is n0 times k plus 1 of what? And k plus 1 up to t minus 1. Right? And this is, so we would have a number of operations which is proportional to this quantity when you compute the product using this forward accumulation. Right. So as I said, we could have done things in the opposite direction. So this is what we do. Let's take this one again. Duplicate. I will share these notes with you after the class. So you can either take note yourself, but you will have access to these notes as well. So we could have done the reverse or backward accumulation, right? And here what we would do is that instead we would start with the product here at first, right? This one. And this would result in a matrix of size nt times nt minus 2, right? And the computation would, the number of operations would be proportional to nt minus 1, nt minus 2. Then we would be left with this new matrix, which would multiply with the one which is just next to it, right? And the computation here, that second computation would be proportional to nt. nt because, again, now what will happen is that the number of rows of these intermediate factors will remain the same and will remain equal to the number of rows that we add in the matrix at the very left. And so now we have nt minus 2, nt minus 3, right? We would have to do that a bunch of times until we arrive here, compute the last one. And here what we would have is the last product, which would have a complexity of nt and 1 and 0. And again, now if you just sum all these numbers of computation, we would have sum, we would have nt, which is common to, you see, as before, we have nt here, and nt here, while before it was n0, which was common to the complexities of times. So we would start at 0 this time of nk plus 1 and 2t minus 2. Okay, does that make sense? And now what we can do is to also rewrite this. So what I could do is that I would rewrite it in this way. It's the same, except that I go only up to t minus 2, right? Plus nk plus 1. Plus the one that I've just omitted, which is n0 and t minus 1 and t. And similarly here, we can do that, but we omit the one for k equal 0. So we'll have nt times k equal 1 up to t minus 2 of nk and k plus 1, right? And then we add back the one we omitted, which is nt and 0 and 1, right? And so why I'm doing this is because now what you see is that, okay, we have these two terms here, but let's just say they are quite irrelevant for our computation. What we have now is that, okay, we have this first term, which is almost the same as this one, except for the factor that we put in front, right? But otherwise, there would be a sum of products over exactly the same quantities. So now you can quickly understand, depending on the value of n0 or nt, one will be better than the other. So let's go back to the slide. So in particular, for us, what will happen is that usually, at least in the case of neural networks, nt, which correspond to the dimension of the output, usually will be quite small, because that very often will correspond to the variable which is attached to the loss function, which is a scalar value usually, right? So nt for us in most cases will be just 1, right? And so that will be usually much smaller than n0, the dimension of the inputs, right? And in that case, then if you go back to our notes, you can quickly understand that this quantity then will be usually much smaller, right, than this one. And so this is why in deep learning, usually we will make the computation of the product of the Jacobian in reverse. So we will apply usually backward accumulation because it will be cheaper. But in some other cases, maybe not related to deep learning, you could have an output space which dimension is much larger than 1. And if for some reason it's even larger than the size of the input space, then it could make sense, and I think actually you should do that, it could make sense to compute the derivative using the forward accumulation strategy. So what time is it? So it's already 10. I think we'll make a short break of 10 minutes now. So let's say we resume at 10:15, and we'll see now how to apply this recipe that we've just seen for a chain composition to the multi-layer perceptron architecture that we've seen together last week. If you have questions, again, do not hesitate. Just send them over in the chat. All right, so welcome back. So there was an interesting question from Margot, and so I will just repeat the question. We just talked about forward accumulation and backward accumulation. In the case of generative adversarial neural networks, GANs, which is, by the way, something which we'll see later on, but which is applied to images, then there would be a first convolutional neural network, a ConvNet, that will try to label images, and then another neural network that takes input a random vector and create images. And then the question is, then this second neural network will use forward accumulation to compute the Jacobian. So just if you, so what is the GAN? First, I will just try to explain very quickly. So the goal of GANs is to have a neural networks that takes as input some small vector z, and then this network would be architectured in some way, which we'll see later on. But let's say it's like this. And what is specific to this network is that this output here is an image of size, of some size, right? And so, of course, in this case, if you wanted to compute the, so let's call this h. If you wanted to compute h, the Jacobian of h, the output of the network with respect to z, when h, the dimension of h is much larger than z, then yes, you should compute the gradients using a forward strategy. However, this is not the end of the story when it comes to GANs, because this output of that first network, which we call G, will be fed as input to a second neural network. And so that second neural network, which is usually a classifier, will take as input the image, does something, but at the end of the day, will collapse everything into just a single scalar output, which will correspond to a probability estimate. But so this final output here has a dimension of 1. And when it comes to adjusting the parameters of this one, the first network, what you do is that you do it with respect to the loss of the second neural network. And so you would do it by going through first the generator and then the second neural network, and then you pass this quantity to a loss that gives you another scalar value. And that's how then, that's the objective that you would like to, in this case, maximize. But then the gradients that you will need are the ones that will actually, so let's say this gives you some y values. You will pass this to some loss, compare that to some ground truths, right? But so the gradients that you will need are those which, when you are the gradients of that loss with respect to the parameters of the first network. And so in that case, we are back to the setup where the actual output of the computation is small, because this corresponds to a scalar value, even though the output of that first network was large and supposedly much larger than z. Also, actually, it's not yeah, it also depends on the size of the parameter, which is more important here. But so even in this case, we would use backward accumulation or backpropagation to compute the gradients. But there might be other setups where you are really interested by this quantity, right? And not by for example, this one. And so if you really care, you want to do something, and you want to obtain these quantities as fast as you can, or this reasonably fast, then you should go, in this case, for forward accumulation. So another question, NT can be interpreted as the final dimension of the loss in deep learning, which is usually a scalar. Yes, that's correct. Yes, and that's what we'll do in just a few slides. All right. So let me just take this, move it to the new page. All right, so just also to give you a quick recap, what we want to do today is to compute Jacobians, which are generalization of derivatives for functions that takes as input vectors and would produce as output other vectors, right? And they are defined as this matrix of partial derivatives. We started with the chain functions that can be decomposed as chain compositions, so in which you just have some you are nesting functions into each other in this way. And then through the chain rule, we saw that you can express the Jacobian of the output with respect to the input as a product of intermediate Jacobians, which correspond to the Jacobians associated to the intermediate functions fk with respect to their output and their immediate input. Then what we have seen is that, okay, now we want to compute this product. There are multiple ways to do that. Two of them are given here on this slide. You could either compute the expression forward by starting by the end, or by starting by the Jacobians corresponding to the first variable in the composition, and then going on from this variable to the output variables and multiplying in this way. Or you could do it in reverse by starting by first computing the product of the Jacobians associated to variables at the end of the composition, and then multiplying from left to right with the Jacobians associated to the intermediate and then to the input variables. And in terms of complexity, so one will be better than the other depending on the dimensions of the inputs and the outputs. Usually when nt, so the dimension of the output, is much smaller than the dimension n0 of the input, then you should prefer backward accumulation, and vice versa. If the dimension of the output is much larger than the dimension of the inputs, then you should prefer forward accumulation. All right, so let's see now how we could use this in the case of the multi-layer perceptron architecture, which we have seen together last week. So you can generalize the chain compositions by just saying that the variables xk, right, they are the result of some function fk, which now takes as input two arguments. The first one is the value of the previous layers, so the previous intermediate variable xk minus 1, sorry. And the second argument are parameters that are associated with fk, right? And we would have that for k equal to 1 up to t. And we would denote by theta k minus 1, for example, all the parameters of these functions. X0 would be the input of our multi-layer perceptron, and it would be given, right? And here, then, and this is what you already asked with your questions, ft, so the output, the final the final function in the composition, usually in supervised learning, would correspond to a loss L, for example, the mean squared error, the binary cross entropy, or others, which would produce as output a scalar value, right? And so therefore, for which nt would be equal to 1. And so in terms of graph of computation, we would have now something like this, where the nodes represent variables, either input data or parameters, and the blue boxes correspond to these functions. So let's see, for example, how we could define a multi-layer perceptron in this way, and then use our chain rule, for example, reverse accumulation, and it would compute this product given by the chain rule using reverse accumulation in the case of the MLP and in the case of some of the parameters of this MLP. Right, so let's just do that. So let's say that we start with some x0, which would be our input data, right? Then this, in the case of an MLP, you would usually multiply this value with some matrix, right? And you would do that through some function f1. So you would connect this one, you would have the first set of parameters, theta 0 or theta 1. Yeah, it does not really matter. Let's just call it theta 1, and I will fix my slides. Then this produces some intermediate quantity x1, right? Then let's say this is then fed to a second function that also takes some parameters, theta 2. Then that will produce x3, which you feed to some function f4, which takes f1, f2, oops, sorry, f3, 3, then that produces x4. No, sorry. F2, of course. Sorry. So F2 produce x2. Yeah, now that makes sense. F3 then produce x3, which is fed to f4, right? Takes some other parameters and produce some output, final output, x. And so, for example, what we would have is that x0 is equal to x, which belongs to Rn0. Then we would have x1, which would be, so f1 times x0 times some parameters, usually a matrix, right? And the computation we would do in the first steps of the computation of the MLP is, for example, to compute this matrix vector product that would produce another vector output. Then we would have x2, which would be equal to f2, which would be the result of the computation of f2 given as input x1. And then usually after this first computation, usually we would pass that through an activation function. So for example, a ReLU. So we would not have anything here, right? What we would just do is to compute, for example, the sigmoid or the ReLU activation of x1. Right? Then we would go on. We would have f3 taking as input x2, and then some parameters, w3, and we would produce w3 times x2. That would then result in what we want to do. For example, let's say we want to come to, so maybe I should draw this. So let's say this is x0, then we would have our neural network, which is like this, which would then produce the term x2, right? So we would make the product and then the activation, and then we would compress that into a scalar value, which would be x3. Right? And then up, and this one belongs to n0. And x2, well, it's the dimension of x2 depends on the number of units we would have put here in our first layer. Right? Then x3, and then, so x3, we would interpret that as our predictions. And then we would compare that through against some ground truth value, which we would have computed as through some function f4, taking as input x3, and here not taking as input a parameter, but some ground truth. And for example, the loss would be x3 minus 1, so the squared error. Okay. Right, so this is just a regular multi-layer perceptron, which I've just redefined using this notation, so as a chain composition. So I will also add the dimensions of all these variables to make things a bit easier. So the dimension of x0 is the dimension of the input data, right? Then here for theta 1, we would have the matrix W1, which is of size R and 1 times N0, right? Where N1 would define the number of units in the layer of the MLP, right? So here would compute W1 x0, and that would produce an output x1, which size is Rn1. Okay. Then we would pass x1 through the sigmoid activation, and so in this case, theta 2 would just not be there. Right. So f2 would be the sigmoid activation that produce another quantity which size is a vector of size n2, right? But in this case, this would be a vector of size n1, because you don't modify the dimension when you pass a vector to the activation function. Then theta 3 would correspond to our matrix W3, which in this case would be a flat vector dimension 1 times n2, right? Such that when you, so this is, right? Such that when you compute W3 times x2, what you obtain is a vector now of size, no, it's not a vector, sorry, it's a scalar, right? Because you would multiply in the matrix of size 1 times n2 by a vector of size n2 times 1, so that the result of this product is a scalar, so just 1. Then here, for theta 4, we would have y, which is a scalar. Then the result, so that would be or loss. And finally, the result would be a scalar. Okay, does that make sense so far? So I know it's a bit laborious, but this is really my motivations today is to try to make you understand from a very low level point of view what really happens when you try to compute the gradient, for example, of the loss that would have here with respect to some parameters. And of course, you can quickly, now I hope you understand that it's quite tedious, and so if you were to do that for much complicated neural networks, you would have a hard time doing it, and it would be quite error-prone. So there is a question from Stefan. Why was x1 left out of the schema? Why is it left out? Oh, it's still there. Ah, sorry. Yeah, the MLP, I suppose. Okay, here I've not, in this one, I've not put x1 because it's some intermediate variable, but if you wanted to be to show everything, what I should have drawn instead is let me erase that. We would have right x1, right, and then we pass this through the sigmoid, and that produces the vector x2, right? And the same here we have the loss. We pass y, and that would produce x4. Oops. Okay. And so now it's a bit different from before in the sense that we don't have we don't have a pure chain composition where we would like to go from x4 to x0, right? Instead, the kind of things we want to compute is the gradient of x4, for example, with respect to the parameters value θ1 or the parameter values θ0, right? But these two things can be viewed as two chain composition. So we have a first chain that starts at x4, sorry, and then would go up to θ3. And here, the value that would be needed here could be assumed as a constant, right? So it's no longer an argument, it's just some quantity which is fixed. And now we are back to the previous case where we are dealing with a chain composition and we want to compute the Jacobian, for example, of x4 with respect to the input, which would be θ3. And we could do the same for the other parameters, for this one, and we would arrive here. And again, we could assume that this one is constant because this is data which is given. And again, we would be left with a chain composition where the output is x4 and the input is θ1. Right? And here in this second chain, we would need values, of course, also for θ3 and θ4, but similarly, we would say they are just constant. Right? So effectively, the functions, the intermediate functions, f1, f2, f3, and f4 would just depend on one argument. All right. So let's do that. So we want to compute, for example, the Jacobian of x4 with respect to θ3, and also Jacobian of x4 with respect to θ1. Right? These are the two things we would need if you wanted to run, for example, stochastic gradient descent, because you would need to adjust these two parameters. Well, so let's start with the first one. So we would have this guy here, which by the chain rule correspond to theta, the Jacobian of x4 with respect to its immediate input, the input associated to f4, which is x3, right? It's this one. And this quantity here for θ4, it just assume constant. So just freeze it. Times Jacobian of x3 with respect to θ3, right? And that's it, because theta 3 is an immediate argument, the immediate input of the function f3. Right? It's an immediate, so theta 3 is an immediate input to f3. Right? So that means this thing is equal to some matrix, right, whose number of columns, whose number of rows is equal to the dimension of x4, so of the output, so 1. And the number of columns is equal to the dimension of x3, which is 1 also. Right? So we would just have one single element here, and this would correspond to the derivative of our loss, this one, with respect to x3. Right? And so that would be equal to x3 minus y. So there is one question. What is phi in f2? It's just to say that this is empty. There is no argument, right? Because f2 here is defined simply as an activation function like the ReLU, and this does not depend on any parameter, right? I'm just using these formalisms to show you that you can express an MLP in terms of the chain compositions that I've defined in the slides previously. Right? So let's go back to this. So the Jacobian of the output with respect to the parameters theta 3. So we would have this now this second factor, which would be a matrix of dimension equal to the dimension of x, where the number of rows would be equal to the dimension of x3, which is 1, and the number of columns now would be equal to the dimension of theta 3, which I will denote in this way. Because what I said is that theta 3 was defined as some matrix in R 1 times M2, right? And so when I denote, when I use this notation, what I mean is that this would be equal to N2, right? So when I have parameters that are matrices, I will just flatten them as vectors. You can extend all these formalisms to matrices and actually tensors of arbitrary dimensions, but this is not really needed for you to understand what's going on. So I will just assume that I can flatten my matrix as a vector, right? And therefore the gradient, the Jacobian I would need to compute, so the second term would have a number of columns which is equal to the number of elements in this vector, which in this case would be N2. Right? And then what do we have to put as values inside this vector, this Jacobian? So if you just look at what's happening, what we said is that x3 was computed as this product, right? And so in this case, that would be some flat vector W2 times some column vector x2, right? And so this is nothing else than just the sum over the elements in this vector, and you take the sum of the product of the corresponding elements. And so, boom. If I say that this is the element I in this matrix W2, then I would multiply this scalar value in this case by the corresponding element in x2, right? And so now what we want here is just, for example, x3 with respect to one of these WTI, right? Which is, you can consider as one of these inputs which is needed for the computation of the output quantity x3, right? And this is nothing else than x2i, right? And so here what we would have is that this vector is just equal to x2 1, x2, and how many elements do we have? We have and 2 of them. Okay. By the way, you should note that in order to compute this second factor, I need to know the value of these intermediate variables, this x2, which happen here in the middle of the MLP. So that means when you do, but I will elaborate on that later on, when you compute the backward or the reverse accumulation, you will need the intermediate quantities that you have computed when you evaluate the function, the original function forward. So you are not allowed actually to discard this intermediate value x2, x1, and the others, because you will need them when you want to compute, for example, this factor in order to compute then the Jacobians that you want. So there was a question, what does that mean? Yeah, it just means I'm doing I'm doing some general matrix multiplication, right? So I consider that this is a matrix of dimension 1 times n2, and this is another matrix of dimension n2 times 1. All right. And so we can compute this. So with this term, we can compute this because we also do know x3. We know the values of y. And so now we have everything we need to actually compute this quantity, right? And that would give us the expression of the Jacobian with respect to theta 3. Or not really the expression, the value of the Jacobian at this point. All right, so that was easy. Let's now do the same for x4 with respect to the other parameters of our MLP, this guy. So again, I will use the chain rule, which says that I can re-express this Jacobian as a product of Jacobians associated to the intermediate functions. Oops. So we have this. X2. You should note that here now the second factor is different from before because we need to go further through the computation. Right? And now theta 3 is considered as a constant, but we need to backpropagate through x2. x1, and then finally x1, which depends on the parameters that we care about, which is theta 1. Okay. So let's do this. So this is a product of Jacobians that we can evaluate. So we would have, as before, the first matrix of size 1 by 1 with x3 minus 1 as its single entry. Then for the second one, we would have the number of rows which is equal to the dimension of x3, the dimension of the numerator, which is 1, but a number of columns which is equal to the dimension of the input, x2, so n2. Yep. Then the second one would be the dimension of the output, x2, so n2 times the dimension of x1, which would be n2, n1, which, if you remember, at this point, what we are computing is the result of the ReLU activation. And so n1 and n2 are actually equal, so this is a square matrix. And finally, the dimension of the output n1 times the number of parameters, which maybe is plenty of them. And so again, I will use this notation. Oops. Theta. And theta 1, what we did I said that theta 1 was equal to some matrix W1 S of size n1 times n0 of size n1 times n0, such that the dimension of n1 is simply equal to the product n1 times n0. Right? It's just I take my matrix and I flatten it into a single vector which is very long with a size of n1 times n0. Okay, so there is a good question. For the first Jacobian, I didn't understand how we know the values of x2. Okay, so let me explain that before we go on with the other derivation. So, yes. So we just derived the expression for this Jacobian, right? And what we arrive to is to this vector, which is the vector in which each element corresponds simply to the values of the x2. And so so where do we get these x2 values from? Well, they are values that you compute when you evaluate the function forward. So when you apply this sequence of elementary operations, you start from x0, then you compute x1 from x0 and the value of the parameters, right? And then you store this value x1. And then from this, you go on, you compute x2 as the output of f2 for values x1, which you have stored, so that means you can compute, right? Using the ReLU activation. That gives you the value x2, and then in your computer program, if you were to implement this, you need to store this value x2 somewhere. Because what will happen is that, okay, you will go on, compute x3 and x4, and then derive the expression for the Jacobians of, for example, the output with respect to the parameters theta 3, and then you would arrive to this, right, in which you actually need back the values x2. But that's fine because you have stored them. Right? So this is how you know these values, because you need to store them when you apply this scheme backward. All right. So this bigger expression. So this is the same as, so the first factor is the same as before. Then here, let me remember. Yeah. So we can apply the same. So we would have again this kind of computation to compute x3, right? Except that now we want to compute the Jacobian of x3, not with W2, with respect to W2, but with respect to x2. And so we can do the same, and what we derive is to a vector, right? But in which the elements are not the x2, they are the W2i. Right, so each element here would correspond to x3 times x2i, or j, let's call it j. I don't know what I used there. Yeah, let's use j's for the columns. Right, and this corresponds then to W to j. Is that correct? No, it's 3, no, W3. I don't know why I put 2s everywhere. Okay. Now, so that's it. We have the second factor. Now the third factor, this one, right? So it's a square matrix. And what we have actually is that, so we are applying the element-wise ReLU or sigmoid activation function, right? And so what we have now is just a bunch of parallel compositions. And so we would have as many as the size of n1, and we have n2. And for each of them, we would compute. So here, what we would have is x1 j, and that would correspond, this one correspond to x2j, right? So that means if you compute the derivative of x2, no, sorry, the Jacobian of x2 with respect to x1, actually that matrix is full of zeros except on the diagonal, because the computation of the element of x2j only depend on x1j, and it will not be affected by the other values of the elements in x1, right? So to make things easy, let's say that our activation function is the ReLU, right? And we are in a regime where x1 is positive. So if you remember, then we are, so if you remember the shape of the ReLU, it's something like this, right? 0 there, right? So if we are now in this regime, that means that x2 is equal to x1, because we are there. And so that's just a straight line, and the slope of this line is equal to 1. Right? So here, what we would have is the identity matrix. Of course, you could say that the sigmoid activation, we just use instead of sigmoid activation, that you would have an expression of the derivative, and you would fill in simply the entries of the diagonal with the value of the derivative, which would be, if sigma denotes the sigmoid, it would be equal to 1 minus sigma for entries x, which correspond to the to the x1s. Okay, and then finally, now we have this guy over here, the last factor, in which we have, so that's a bit more tricky, but so what we do here is that to compute x1, we said that we would multiply x0 by the matrix W1, right? So here that would correspond now to a matrix of size n1 times n0 times n0 and then 1, right? And that's equal to this kind of vector of, right, which is over x1. Oops. Okay. And so what we have is that this, for example, if we take, oops, sorry, wrong pen. If we look at the entry here, the element I in the vector x1, right? This element I is actually associated to this row in the Jacobian, right? And how is this guy computed? It's computed as the product, as the dot product of these elements with this element, right? So what we have is something which is very similar to the previous case, where, for example, xi, x1 I is equal to W, let's sum of the W, so 1, that's the matrix. And then we select the row I and we take all the columns. This is what this is what this column means. And then we multiply this with the corresponding value. No, it should be J. No, wait. No, it's I. Up. Times x0 I. Right? And so that means the value of x1 in the element I only depend on a subset of the values in the W1 matrix, right? Which are these ones. So that means this guy over here will be a long vector which is mostly made of zeros, because there are many entries, all these ones and all these ones which will not affect the value of the corresponding output, right? So it will be, in this case, a vector like this, made of several segments, where we will have 0, 0, 0, zeros, almost everywhere, except for a segment in which we would have then the values of the x zeros, this one, oops, so this one, because what we would then need to compute here is x1 I with respect to all the wij, right? This is the values that you need to compute everywhere. But many are just zeros, except the ones associated to these values there, right? And this right? And so that means here we would have a segment, a vector, or a subvector in a sense, which would correspond to a vector x0 itself. Okay? So there is a question, I think it's a sum of J, yes, yeah. I mean, the expression is correct, but I just switch again, sorry, the semantic of I, but you should switch over up and then J. Yes, that's correct. Sorry, I know what's wrong. You select the row I, but you then select the column J. Like this. That's correct. Okay. So this thing here would look like a matrix in the end, which is x0, x0, for example, x0. If x1 has a size of 3. And everywhere it would be zeros. Okay? And so this is what I said. You can actually generalize all this formalism to matrices or tensors. And I think, if I'm not mistaken, you can rewrite the same expression simply as a Kronecker product, which is written like this, which would correspond to this matrix. Okay, so that's it. We have computed all of our factors, and now that we know how to compute them, we can finally take their products and, for example, using the backward accumulation scheme. And that would give us, finally, the value of the Jacobian that we need then to plug in when we do stochastic gradient descent. Okay, so let's go back to the slides. You have questions on this? I think it's a good exercise if you just try to do it yourself by hand on paper at least once, so that you quickly understand that it may look a bit complicated, but it's very mechanistic in a sense. Just look at individual functions and then every time try to compute the Jacobians of the variables that they produce with respect to the variables that they take as inputs. So this is done. Right. So now we can finally move on to computer programs, because of course, in most cases, we will not be able to express the computation that we want to perform as a chain composition of this form, right? So we'll basically now generalize our framework to arbitrary computer programs. And so we'll say that we have some function f, which still produce as output some vector value, right? And this function will take as input a bunch, s of them, of vectors, x1, x2 to xs, right? So the vectors x1 to xs will represent now our input variable. Then the computation of f will itself be implemented by a computer program that produce intermediate variables xs plus 1, xs plus 2, up to xt. And t here will correspond to the total number of variables that we'll have to compute, where the final variable xt is our output variable, right? So effectively, when I will say, so effectively f of x1 to xs will produce a value which is equal to xt, right? And again, I will use the same convention. So xk, so any variable, either input, intermediate, or output, will be represented by a vector of size nk. And then our goal will be to compute the Jacobians of that function with respect to any variable xk, so either the input or the intermediate variable. Well, no, sorry. Here I've just mentioned the input variable, so for k equal 1 to s, but of course to do that we'll need the intermediate Jacobians for corresponding to the intermediate variables. All right, so we can basically express this as something which is very close to our chain composition, because in a sense, when you consider a numerical algorithm, you can view that as a succession of instructions, and each one of these instructions is something which looks like this. It's at every step, what you do is that you produce a new variable xk, and this variable xk is the output of some instruction fk, taking as input all or a subset of the previous variables, so from x1 to xk minus 1. And then you repeat that, of course, for different functions or operations fk, but otherwise it looks very similar to what we had before, except now we have extended the set of arguments of our fk instructions to more than just the previous variable xk minus 1. So in a sense, what we have is the following setup, right? Where we have input variables x1 to xs. We compute one by one some temporary variables, and each of them depend on a subset of the others, of the previous ones, until finally we produce a final and special variable, which we call the output, and which is denoted as xt. So when you view it like this, what we've just done is to represent the computation as a directed acyclic graph, right? Where the nodes in this graph are our variables xk, and there is an edge between, so from xi to xk, if xi is one of the arguments of the function fk associated to xk. Right? And so this directed acyclic graph is what we'll call the computational graph, or the graph of computations of associated to our function. And in this mindset, then the evaluation of the output xt just corresponds to a forward traversal, so from inputs to outputs of the graph. Right? So before when we considered chain composition, we also had a graph of computation, but it was much simpler and represented in this way. What I am now saying is that for any variable, for example, not this one, but xt, it could depend on the previous one, of course, but also it could depend on any of the other ones that you've computed before. So you would have just more arrows between nodes. Of course, it should be acyclic, so you could only okay, so yeah, it should be acyclic. So of course, the computation of some variable xt could only depend on variables that have computed before and not depend on variables that will be computed afterwards. All right. So now we'll see that there are two ways to apply the chain rule. I mean, there are not two ways, but there are two main ways to apply the chain rule, and which is very similar to what we did when we consider the forward accumulations for the computation of the factors, and the reverse accumulation the other way around. So we'll start with the forward mode. And so the forward mode of automatic differentiation simply consists in computing the Jacobians of the variable xk with respect to x1 for all variables xk starting from the first intermediate up to the output xt. Right? And in this way, you would then be able, if you compute them iteratively one after the other in this ordering, eventually you would arrive to the computation, to the Jacobian, which corresponds to the Jacobian of xt with respect to x1. And remember, this is our goal. What we want to compute is are the Jacobians of the functions, so which is xt, with respect to any of the inputs x1 to s. Right? So here you would do it once for x1, but then you would have to repeat that for x2, x3 to xs. Right? So how does it work? So the first step is to initialize the Jacobians associated to the input nodes. And so what you would do is that, so if our goal is to compute the Jacobian of xt with respect to the first one, so x1, we would set the Jacobian of x1 with respect to itself, to the identity matrix of size n1, and then we would set the Jacobians of the other input variables, so x2 to xs, with respect to x1, to matrices which are zeros and of size equal to n2 times n1, n3 times n1, and up to ns times n1. And then, given this initialization, what we can do is to apply what is called a forward recursive update. So for all k from s plus 1 to t, what we'll do is that we'll compute the Jacobian of xk with respect to x1. How? So what we want to do is to compute the Jacobian of this variable here with respect to x1. And so we'll apply the chain rule to do that. So we'll iterate over the parents of xk, which we call the L variables, right? And by the chain rule, we know that we can express this as the sum of the parents of the product of the Jacobians of xk with respect to the parent, so its immediate input, times the Jacobian of that parent with respect to x1. Right? So before we had the same, except that we always add only a single parent. So xk depended only on one single other variable, previous variables. Now we generalize that to more than one arguments. And so if you do that, then you need to rewrite, you need to generalize the chain rule in this way. So there is the sum which appears for the parents, but otherwise it's the same term. Right? So here in this expression, I denote with this bracket notation the on-the-fly computation of the Jacobian, which is locally associated to that node, or rather to the function fk, with respect to its argument xl, with respect to the L argument taking the value xl. Right? And this second factor here, so the Jacobian of the parent with respect to x1, is actually obtained from before, from the previous iterations, right? Because we start from these initial values, and then we build them one by one. So that means once we are considering this node, we have already computed the Jacobians of the parents with respect to x1. Okay, so this, for example, this Jacobian here, this term is already computed, right? So now you can move and proceed forward and evaluate then the value of this whole expression and store that somewhere, and that would represent the Jacobian of xk with respect to x1. What time is it? Yeah, I think it's time to make a second break. I will try to speed up a bit, but it's best, I think, still if we make a break. So let's resume in 10 minutes at 11:30, and we'll see. I will run this. We'll run this algorithm together on a simple example. All right, so welcome back. So I will start with a quick recap of where we are and what we want to do. So what we just did before the break was to express numerical algorithm as directed acyclic graphs of this kind, in which nodes represent, for example, input variables, output variables, or temporary variables that you need in order to compute the output. And each one of these variables, the temporary or the output variable, is computed by some function fk, which is basically defining how the creation of a new variable xk as the application of some function with respect to some of the previous quantities, some of the previous variables, right? So one of the inputs or some of the temporary variables. Okay, and then I said that, okay, then we would like, for example, to compute the gradients, the Jacobians of, let's say, the output with respect to the input, right? So in the case, for example, of deep learning, these inputs would be the model parameters, right? And so you can also apply the chain rule on this graph, except that now it would be a bit different in the sense that you need to account for all paths in the graph of computation that connect the quantity that you want to differentiate. So for example, xk, that connect this quantity to for example, the other variables. So x1 in this case, or one of the inputs, with respect to which you want to compute the Jacobian. Right? And so there is a first way to do it, which is given by the so-called forward mode of automatic differentiation, which consists in which the goal is really is still the same, and the way we do it is by computing Jacobians incrementally, iteratively, from k equal s plus 1 to k equal t. So going from inputs, then through the temporary variables to the output, and you would follow the topological ordering of the variables, right? And so you would initialize the Jacobians for the inputs in this way by either using the identity or zero matrices. And then what you would do is that you would apply this recursive update in which you express the Jacobian of some variable xk with respect to x1 as the sum over the parents, the direct parents of xk, right, which we denote by L, of the product of the Jacobian of xk with respect to this parent and the Jacobian of the parent with respect to x1, right? And here, this second factor would be given from the previous computations, right? Or from the initialization. And the first factor here in the expression is what you actually need to compute locally at the node xk, right? So that would denote the on-the-fly computation of the Jacobian, which is locally associated to the function k for the argument associated to xl. So let's see how to apply that. So we'll go back to an example on the iPad. Oops, I need to reconnect it, of course. Okay. So this is the example we'll consider. Let's say we have a function which depends on two variables, x1 and x2. And just to make it easy, but not trivial, we'll say that the function is defined in this way. So it's the sum of two terms. The first one is x2 times the logarithm of x1, and the second one is the square root of that same quantity. Right? So in terms of graph of computation, you could represent the same, if you were to implement actually this function as a computer program, what you would do is that you would say that you would first compute, you first define a first temporary variable x3, which would correspond, for example, to the logarithm of x1. And then you would compute a second quantity, which would be the product of the logarithm of x1 with respect to x2. And let's say we store this value in x4, right? Then, since you are smart, you notice that this quantity is used both in this term, but also it appears inside here. So we will not compute this one again explicitly, you would just reuse the computation that you just did and that you stored in x4, right? But still you would need to compute the square root of that. So that's what you would do, for example, in a fifth variable x5, which would correspond to the square root of x4. And now that we've computed x4 and x5, we can sum them together to produce another variable, x6, which is the sum of x4 and x5, right? And that would correspond to the output of the function, right? So in our formalisms, right, we would have x1 and x2, which correspond to the outputs, x3, x4, x5, which correspond to temporary variables, and the output, which correspond to x6. So now, let's say what I want to do is to compute the Jacobian of x6 with respect to x1. This is my goal, right? So we'll just run the forward mode of automatic differentiation. So the first step is to initialize the Jacobians. So you would do it for x1, and we said you would initialize it to some identity matrix, and you would initialize the other one, so the Jacobian of x1 with respect to x2 to 0. And then we would proceed forward, so from x1, x2, then going on to x3, x4, x5 to x6, right? And so at every step, we would compute the Jacobian of the temporary variable, so first x3, with respect to x1, right? So we would apply, so in this case, x3 has only one parent, right? So that sum that we had in the recursive update, in the forward update, has only one term, and this term is x3 times x1 over x1 times x1, right? And this quantity here is something that we know from the previous iterations, right? And it's this one here. So this would be equal, so x3, let's assume everything is correspond to scalar values to make things easy. So that we would want to compute the derivative of x3 with respect to x1, given that x3 is the log of x1, so the derivative is 1 over x1 times 1. Okay? Maybe I should just give you back the recursive update that you would apply so that it's easier to. So what you want to do is to apply recursively this, which is defined parents of x L times xl times x1. So this is the rule that we apply. Right? So when I was considering this one, x3, also, the set of parents of x3 is just made of one parent, which is x1, right? So look at things like this. x3 depends only on one guy, which is x1. Then we can do the same for x4 with respect to x1, except that now x4, right, has two parents, x2 and x3. So what we will have is that the sum is made of two terms. So let's consider the first term. So x4 with respect to its first parent, x3, times the Jacobian of x3 with respect to our target x1, plus for the second parent, x4 with respect to x2 bim times the Jacobian of the parent with respect to x1. And that is equal to so x4 so we would have what we want is the derivative of this product with respect to x3, which is x2. Right? So this is equal to x2 times this, which is that. Right? So I will just keep it there, times x3 plus now we have to compute this, but from the initialization we do know that this guy is equal to 0, right? So the whole thing is equal to 0, and that's it. Plus 0. Okay, moving on. There are two more to compute. So this one, x5, is the square root of x4, depends only on x4, so only one parent. So we would have x5, 4 times Jacobian of x4 with respect to x1. And this, so the square root of x4, we take the derivative of that, so that's 1 over 2 times 1 of x4 times this guy, which we've just computed here, right? And finally, x6 with respect to x1 is the sum of x4 and x5. This, so this one is the sum of x4 and x5. So two parents, and we would have that it's equal to x6, the first parent is x4 times x4 x1 plus the second parent x6 x1 okay, and so x6, which is defined simply in this way as the sum of x4 and x5. If you differentiate with respect to x4, that gives you 1 That's 1 times x4 x1 plus the same for this guy, right? And these two factors here, we have them. So x4, this one is given here, and this one is given there. So there is a question, since we are calculating the derivative with respect to x1, shouldn't it be the derivative of x2 with respect to x1? Yes, I think you're correct. Thank you. Yes, that's correct. Thank you. I'll fix that. So here it should be like this. Yes, thank you. And it is what I did there, right? And not the other way around. Okay, so now what we just did was to compute using this forward update the derivative of x6 with respect to the first input x1. And so that means we would have to repeat this whole thing. For example, if we wanted to compute now the derivative of x6 with respect to the second input x2, right? So I think it's a good exercise for you to do it. I will not do it because I'm a bit short on time, but you would just apply the same algorithm and you would obtain the value for this Jacobian. Okay. Oops. So this is a correct algorithm. It will give you the right answer, but the first thing we could say is that unfortunately, we would have to repeat forward mode automatic differentiation for as many inputs that we have. So if S, the number of inputs, is large, this might be quite prohibitive, right? This will be expensive to run. However, there is still a nice thing to say about this algorithm is that the cost in terms of memory is actually quite limited because we are computing in parallel the forward path and the gradients, the derivative of Jacobi, right? Because as soon as you have computed, so what happens is that the temporary variables, they can be freed as soon as their child nodes have all been computed. So when we were computing for example, the partial derivative of x3 with respect to, or the partial derivative of x4 with respect to x1, to do that, we needed to know the partial derivative of x3 with respect to x1, right? But as soon as you have used it to compute the partial derivative of x4 with respect to x1, then that term that you computed before for x3, you can discard it because you do know you will not have to use it anymore. And so in terms of memory budget, this can be quite interesting because you don't have to store all these temporary variables. Just basically keep a fringe of temporary variables that you need because you know they are still connected to variables for which you have not yet computed these Jacobians, but as soon as you've computed them, then you know that you can remove them from memory. All right, so as you have guessed, you can run this algorithm forward. If you can run this algorithm forward, you can also run it backward. So this is what we'll do now. So instead of evaluating the Jacobians of xk with respect to x1 for k increasing from s plus 1 to t, the so-called reverse mode of automatic differentiation will instead consist in computing the Jacobian of xt, directly the target, right, with respect to xk for k going down recursively from t down to 1. Right? And so the initialization, now we'll just consider one node, which is the Jacobian of xt with respect to itself, xt, and which corresponds to the identity matrix of size n t. And then we can make use of the chain rule, but in the other way around, to express the Jacobian of xt with respect to some now intermediate variable xk. So what we want is to compute the Jacobian of this variable x. We want to compute the Jacobian of xt with respect to this variable xk, right? And so this can be expressed as the sum, as a sum over the child nodes of fk, right? So over the child node m of xk, and at so each term then would correspond to the Jacobian of xt, the target, with respect to this child intermediate variable, so the xm, times the Jacobian of xm with respect to xk. Correct. Yes. Yes. Right. So it's the same as before, but in the other way around, basically. And again, what we have is that we have some factors in this expression that are known from previous computations. Now they will, these factors will correspond to the Jacobians of xt with respect to the child xm, right? Which we obtain because we are traversing now the graph in reverse topological order from the output back to the input, right? And these quantities in the literature, in the scientific literature, is called the adjoint vector. Then this bracket notation again will denote the on-the-fly computation of the Jacobian, which is locally associated to the primitive fm. So for when that you need that you have used to compute fm with respect or using the values xk. Right, that's one of the arguments. All right, so we'll just now run the same algorithm, that algorithm, the reverse mode of automatic differentiation, on the same graph as we just did for the forward. So let me copy this. And that will be the last development for today. After that, it's just bonus. Backward mode of AD, and that's slide 20. So same problem as before, and we'll just follow the new recipe, the one of reverse mode automatic differentiation. Backward. So we'll apply this backward recursive update over the graph. So the first step is to initialize. So we still want to compute the Jacobians of the output with respect to the inputs, right? And so the recipes tells us that we should initialize a first Jacobian as the one associated to the output. So we would initialize x6 with respect to itself, right, which is an identity matrix. So in this case, let's just say everything is scalar. And then we traverse the graph in reverse, right? And so the next node to compute, the next Jacobian to compute would be the one associated to x5, right? It would not be x4, right? Even though it's directly connected to x6, because to compute x4, you would need also to have computed before x5. So the next x6, and maybe I can write down this to make things easier to follow. So what we would do is that at every step we would compute xt with respect to xk as the sum m for the children. Oops. Okay, as t m times okay. Okay, that's the backward update that will now apply recursively to compute the terms that we need. Okay, so the first one will be x5, right? So x5 has only one child node, right? Which is 6 itself. And so in this case, we would have x6 with respect to itself times x6, the child node, with respect to x5. Okay, and so that's equal to so this one, which we know from the previous iterations, right? This is the adjoint vector. So in this case, it's equal to, it's given by that, times the thing that we compute locally at the function f6, right? Which is, in this case, this one. So the derivative of this with respect to x5 is equal to 1. Now, the next one, x6 with respect to x4, the next node in the reverse topological order. So x4 now depends on two child nodes. So we would have first xt with respect to x5 times x5 with respect to x4 plus x6 on target with respect to the x6 itself again, because x target is an immediate child of x4. And then it would be, oops. Okay. These two vectors we do know from previous iterations, right? It's this one and this one. And now x5 with respect to x4. So x5 is this square root of x4. So it's equal to 1 over 2 of 1 over x4 plus x6 with respect to itself. So that's the thing we know from initialization. And x6 with respect to x4. So x6 is the sum of x4 and x5. So the derivative is 1. Okay. Now, next one, which is x3. Boom, x3. x3 depends on has only one child node, which is x4. So we will have x6 times x4 times Jacobian of x4 with respect to this variable x3, right? The first factor we do know from before. That's just what we've computed at the previous line. And x. So x3 is the product x4 is the product of x2 and x3. So if you differentiate that thing with respect to x3, you get x2. Okay. x6 with respect to x2. x2. It's x6 with respect to. So x2, how many child nodes does it have? It's 1, which is x4. x4 times x4 over x. God, yes. That first factor we know. And this one, x4 respect to x2, that's x3. Right. And finally, x6 with respect to x1 is equal to x3 times pim x3 with respect to x1, which is equal to x3 is the logarithm of x1, so it's 1 over x1. Okay, and so that's it. Now, what is different from before is just in just one run of the algorithm, right? We have obtained both gradients, both Jacobians. So the one with respect to x2 and the one with respect to x1. While before, for the forward mode of automatic differentiation, we did all of these things just to compute the first Jacobian. And now we get them both in one go. Both at once. All right, so now let's come back to the slides. So this is done. All right, so from this, what you can say is that the main advantage of backward mode automatic differentiation is that a single traversal of the graph allows to compute all Jacobians. And actually, this is true because we assume that the output, we assume just a single output. But if we had several outputs, we would need similarly to run the algorithm maybe several times. However, and this is something maybe which is not obvious is that the cost of that algorithm in terms of memory is significant because we do need to keep all the temporary variables computed during the forward pass. We cannot erase them as we could in the forward mode of automatic differentiation. So the memory complexity of that algorithm is at least as large as the sum of all the intermediate variables that you need to compute in the forward path. And so if you are dealing with very large graphs, for example, big compositions of neural networks, this may be problematic in some cases. All right, so that's about it for the algorithm, automatic differentiation. You see that it's quite mechanistic in a sense. You just follow recursively this update by traversing the graph either in topological or in reverse topological order, right? Or you would apply in the forward mode this update recursively, but by traversing the graph forward. And the only thing that you need to know that you need to know how to do at each step is basically how to obtain the Jacobian, which is locally associated to one of these functions, right? With respect to one of its input. If you do that, then you will obtain this this factor, and then that you will just multiply in with the previous values that you've computed before. And at the end of the day, you would obtain finally the Jacobians that you're after. In particular, the Jacobians of the output with respect to the inputs of the programs. All right. So fortunately, all of this is done for you and implemented for you very efficiently in all deep learning frameworks. So the main ones are PyTorch, TensorFlow, and JAX. In the homeworks, we'll tell you about PyTorch, but you should know that there are other frameworks out there, and the main ones, the other main ones are TensorFlow and JAX. And they all implement some sort of automatic differentiation algorithm for you. But so what is now interesting is that now you should get some understanding about what's going on in this framework and how maybe they are defined, or how or why their API are defined in the way they are defined. So these frameworks, they have all something in common, is that they are basically a library of primitives, of primitive functions, primitive operations that you can compose together. So it's this library then offers, basically represents some kind of language that you can use to express your computer programs, right? And so this is how, by composing these primitive operations, you can define neural networks, but you can also define other programs if you wanted to, right? And so since these primitive operations define basically some forward computation of elementary operations like products, additions, or things that are more complicated, like taking, maybe not, but taking the mean or taking the exponential or all these kind of things, then by just by composing them over and over, you would then be able to express computations that are more complicated. But at the end of the day, they would just be a composition of these elementary primitive operations, for which the library is also defining how it should how it can differentiate itself with respect to its argument, right? And so the library is basically defining what are the functions fm that are associated, for example, by this quantity xm, but also how this function fk or fm can be differentiated with respect to its argument, right? So the framework is defining for each of these primitives how this on-the-fly computation should be performed or is defined. So this is the screenshot in the case of JAX. So what is nice about JAX is that it basically implements exactly the same interface as the one that you have in NumPy. So if you are comfortable with NumPy, you can just in one line replace the imports, which basically typically would be import NumPy SNP with in this case import jax.mp SNP, and now magically the program that you would have written as a composition of these NumPy primitives, which are now JAX primitives, would be differentiable. Right? And so what happens is that the primitive of functions that you use, they would be composed together into a graph that describes the computation. Right? This is what you do when you write your Python code. You just assemble, you compose together these primitive functions in order to compute what you want to compute. And then depending on the framework that you use, the graph of computation, so the one that we need to run automatic differentiation, it would either be built ahead of time, and so there are different ways to do that, but one way would be to look at the Python code and then extract the abstract syntax tree of the program, and then from this derive the directed acyclic graph of computation, right? Or another way would be to explicitly, as part of your program, using a dedicated API, instantiate, construct yourself the graph of computation, and then from this graph of computation, you would then be able to run automatic differentiation. This is how it's done, or how it was done, for example, in TensorFlow 1. You had to build yourself the graph of computation, and then from this, you could then run differentiation. In more modern framework, all of this is a bit now hidden for you, which makes things a bit more natural in the sense that the graph of computation is computed on the fly during the execution of the program. It's computed just in time. So this is how it's done, for example, in TensorFlow 2. When you enable the eager mode, it's how it is done in JAX, and also how it's done in PyTorch that you will use in the homeworks. So what happens there is that you just write your Python code as a composition of these elementary operations. And then as the Python code is executed by the interpreter, the graph of computation is actually built below by the framework. And then from this graph, you are then able to run automatic differentiation on it. All right, a last comment about what really you would need to do if you were, for example, to implement your own small library for automatic differentiation. So if you look closely, for example, if you take the backward recursive update, we could be in a situation which is like this, right? Where we would like to compute the Jacobian of the target, the output with respect to some variable xk, right? And we know already from previous iterations, Jacobian of the target xt with respect to the child xm, right? So in the recursive update, what we said is that we would compute this Jacobian as the product of the Jacobian of xt with respect to xm, so this thing that we know from before, times and what I said is that times the Jacobian which is computed on the fly from the primitive fm associated to this variable xm, right? However, usually what happens is that this Jacobian, if xt is a scalar, which is really the case in deep learning, this Jacobian corresponds to a vector, right? Yeah, it corresponds to a vector. And what we just want to do is to compute this new Jacobian, right? And so you can re-express the same computation as a vector times Jacobian product, which we call a VGP. And in terms of implementation, what will happen usually is that the primitive will not explicitly build the Jacobian that appears in the product, but it will directly compute the vector Jacobian product. And that's usually simpler and faster to do, and also more memory efficient. So if you were to look at the source code of this framework, they would never instantiate explicitly these guys, but they would have primitives or methods to compute this whole product at once. Right? And then usually what happens is that in the case of reverse mode automatic differentiation systems, they would compose these VGPs backward to compute, for example, the Jacobian of the output with respect to some input x1. And similarly, in the case of the forward mode of automatic differentiation, you can express things, you can express a forward recursive update in terms now not of a vector Jacobian product, but in terms of Jacobian vector products. And again, for the same reason, there are some frameworks that implement instead forward mode of automatic differentiation, and they would be defined in terms directly of these operations, and they would not explicitly instantiate the Jacobian that appears in the product. All right, and then I started the lecture by telling you that you can write code in which you can not only differentiate the computer program that you write with respect to some arguments, but you can also compute higher order derivatives. For example, I could write some small Python function that would implement the hyperbolic tangent. Then I would compute, I could use the grad, some grad function that would then run automatic differentiation to obtain or to be able to evaluate the derivative of this function. So this first guy, you know, now you should hopefully understand how it works. It would just run on the fly automatic forward or backward automatic differentiation. Now, what might be a bit more mysterious is what would happen if you take now second or third or higher order derivatives, like if you take the grad of that function. What will happen is actually quite simple. What happens is that you can view the algorithm of automatic differentiation, let's say reverse mode automatic differentiation, as a composition of simple primitives, right? And so that means there is a computational graph which is associated to the execution of that algorithm. And so if you get the graph of that thing, then you can run again automatic differentiation on this graph, even though this graph is itself describing a run of automatic differentiation. Right? It's exactly how it's done. So the backward pass itself is a composition of primitives, and its execution can be traced, right? And reverse mode of automatic differentiation, for example, can run on its computational graph. And that's how you obtain these higher order derivatives. All right, so let's consider a few examples now. Yes. So I will show you some code, and I will show you how to do that in JAX. In the interest of time, I will not show you how to do it in PyTorch, but you will learn how to do that as part of the homework. All right, so let's up. I will collapse this and zoom in a bit. All right. So I will just show you that indeed that works in the way I've shown you. And so I will first, for example, define again that same hyperbolic tangent function. Right? If you are familiar with NumPy, right, I would be using the exponential function from NumPy. Except, and this is an important difference, I'm not importing NumPy, I'm importing the JAX API of NumPy. Right? So this import statement is not import NumPy as NP, it's import jax.np as NP. Right? So I define my function. Of course, I can apply it to scalar values, and the hyperbolic tangent of 1 is equal to 0.76. Right? Nothing very spectacular. I could apply, of course, this thing over a whole range of values, right? And I would obtain for each one of them the corresponding value of the hyperbolic tangent. All right. Now, what I've been telling you is that this, for example, in the case of JAX, the graph of computation would be computed on the fly as you run, as the Python code is executed. And indeed, this is what happens. For example, you can extract the graph of computation that would be associated with my function. And then when it is applied to some value, for example, the value 1. And in this case, the graph of computation, which is represented by this, they are called JAX expressions, would be the sequence of simpler statements, simpler operations, exactly the kind of statement that we did when we did the derivation by hand when we run forward and backward automatic differentiation. And so you see that it takes as input some argument, which has the name of A, and then it computes a first temporary variable B, which is the result of the multiplication of A with -2, right? And indeed, if you go back, this is the first quantity here. And then there is a next temporary variable C, which is the result of the exponential function taking as input B, the previous temporary variable. Right? And you go on until you arrive to a final variable F, which is in our case the output of the function. That's our target xt. All right, so now let's actually run automatic differentiation. So the only thing that I need to do now is to call the grad function, and it's taking as input another function, which is the hyperbolic tangent function. And now this fp is itself a function that I can run at any value, right? So again, if I look at the derivative at 1, so that means before we were considering the value of the hyperbolic tangent at 1, that was this guy, 0.76. Now, if you look at the tangent to the curve and the slope of this tangent, that would correspond to the derivative, which is 0.4, around 0.4. Again, I could just show that for a bunch of values, and so we would have the function itself, and in orange, its derivative. So indeed, you see that's the correct one. For values that are near -3 or below, or near 3 or above, then the function is flat. That means the gradient is close to 0. And then in the middle, the slope increases quickly. That's what you see here in the derivative. There is a maximum at 0, and then it's decreased. So the slope decreases back to 0. Right? And so what happens is that when you run fp at 1, right, there is some graph of computation which is built below. Right? That graph of computation, in this case, I'm using the same function to inspect that graph of computation, would now look like this. And that would actually would run automatic differentiation on my original function, the hyperbolic tangent. Right? And again, what you see there is that this thing is a graph of computation, right? So I can run automatic differentiation again for this particular function, right? So I can take the second or even the third derivative, right? I would just compute them all at once. I would have the second derivative at 1, which is equal to 0.63, and the fourth derivative, which is equal to 0.62. I could show these values for you, right? And you get back the kind of plots that I had at the very beginning of this lecture. And you could do that for higher order derivatives if you wanted. And again, while these second and third order derivatives are themselves compositions of simple primitives, and so when you run backpropagation on this graph, what you obtain is a composition of other primitives, to which correspond another graph of computation, which is this one. Now you see it's getting bigger and bigger, but it's still a composition of simple operations. And the same for the third degree derivatives. You would have a graph, which is now quite complicated, but still a bunch of simple things that you know how to differentiate individually. Just that the composition is getting more and more complicated, but now we let the computers do that for us. And this, by the way, is giving you the exact value of the derivative or gradients or Jacobians, whatever. And it's not making an approximation. All right. So let's back to the slide for a bit. And I will conclude very soon with a few more examples. All right. So now you should know everything that you need to know when it comes to automatic differentiation applied to neural networks. What I would like to show you as well is that this framework does not actually come from deep learning. This is something which has been developed independently and applied to many other problems in physics, in engineering. These are techniques that are known. And this is something I want you also to remember. This is not something which is deep learning specific, but this is something quite powerful in the sense that this is an algorithm that tells you how to basically differentiate through any program. And so there are many applications that you can think of, and I will show you a few ones today. So I will start with this short talk. I will not show it in full, but I've just selected a few minutes of it, where this guy, Ryan Adams, it's his name. With this name, showcase a few applications of automatic differentiation. All right, so let's start.
So what I thought I'd do is tell you a couple of sort of like little vignettes of totally crazy things you can do if you have access to sufficiently powerful automatic differentiation. I'll just sort of zip through a couple of these, but it's fun to just imagine like crazy stuff. So for example, optimizing the optimization process, right? So you might apply stochastic gradient descent to your neural network to train it to learn cats, as we discussed before, but you might have a lot of questions about, what's the right way to set my learning rate? How should I set my regularization parameters? You might have a lot of sort of things that you had to set in an ad hoc way, but stochastic gradient descent, this optimization procedure, is itself a composition of a bunch of differentiable functions. So you can actually backpropagate through stochastic gradient descent to sort of give yourself a microscope, in a sense, to ask questions about how these things might train. So for example, if you've trained a neural network, then you might have faced this challenge of trying to figure out how to set the learning rate for the different layers. Here, where we have access to gradients, we can ask questions like, well, what are the right learning rates, not just for every layer or the whole thing, but for every single time step? What if every single time step of our training had its own unique learning rate? And so you get some interesting insights about the fact that the final layer tends to want to learn really aggressively fast, and the first layer learns a little bit the whole time, but actually kind of the other layers don't really seem to matter that much. Anyway, these are the kinds of questions you can ask that we couldn't sort of ask before. Similarly, there's been a lot of intuitions about how to initialize the scale of the weights. In fact, it sounds like a really trivial thing, but the difference between now and 1992 in terms of deep learning can be a surprising amount of the advances can be explained by realizing that you should think hard about the initialization of the weights before you train the network. So that is like, what's the standard deviation of your initialization? And there's been some intuitions that have been developed that then it was possible to sort of rationally verify.
So maybe that was quick, but just to make sure you understand what that first use case was. So in this case, it's trying to optimize the optimization process itself. So if you remember from last week, we saw stochastic gradient descent, and you apply that. So you just have a for loop, and at every iteration, you make a step, right? And then you proceed for a certain number of steps, like maybe 1,000 iterations, and you obtain some final answer for your parameters, right? But you can view this loop, right, as a sequence along. If you could unroll all these operations, you would have a long sequence of operations. And this sequence is again a composition of simple operations. So that means you can backpropagate through this whole process. So you can differentiate it through, and that means now you can, what they did is that, for example, they would look for, they would backpropagate with respect to number of, but how they would initialize, for example, the weights of the neural networks or other hyperparameters that would control, for example, that would be associated to the optimizer. For example, the learning rate, they could tune the learning rate using by gradient descent as well. And so that means they could, so they are using automatic differentiation to differentiate the optimization process with respect to the learning rate.
Similarly, you can ask really crazy questions like, what if I optimize my training data? Like, what if instead of, what if I wanted to build a like MNIST handwritten digit recognizer, and I let it pick, and I let it identify 10 data examples that were going to be the best ones to improve my validation performance? Then like, what training data would it really like to have? And you can kind of see that it learns some digits necessarily, but kind of funky digits where they tend to be well-defined, where they don't overlap with each other. You can also do some totally wild things that aren't machine learning. So
this one I will skip because I will have a second example. This one I will skip in the interest of time, and I will directly go to this one. So I think it's a very nice use case of automatic differentiation in the case of engineering. So what is done here is that this author basically wanted to optimize for a wing. So it wanted to find what would be the optimal shape of a wing. And the way it did that is that by first writing a simulator for a wind tunnel, implementing fluid dynamics, in which it put in the wind tunnel some obstacle, like for example, initially a rectangle like this. And then from this object would then derive the lift and the drag of the object. And then what he wanted to do was to optimize for the lift, because he wanted to find a geometry for the wing, which of course should not be rectangular, but a geometry for which the lift would be as high as possible, right? And so that's something you can do quite easily in automatic differentiation, provided that your simulation and the computation of the lift is written in an automatically differentiable language, right? But if that's the case, what you can do is that you can just simulate forward the wind tunnel. So you just execute your simulator with respect to the geometry of the wing, and then you backprop through the simulator with respect to the parameter that define the geometry of the wing. And so at the end, what you obtain is something which looks like this, and which looks like really the profile of a wing, even though it started from something very crude like a rectangle. And so in terms of code, this is really just exploiting the power of automatic differentiation. So I invite you to run this notebook if you are curious. So it implements the physics of fluids, so Navier-Stokes equations and so on. It used them to simulate a wind tunnel, blah, 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 blah. So you have a bunch of code to do all of this simulation assuming in this case just a 2D plane, not a 3D simulation, then some more code to simulate the wind tunnel itself. And then that's the interesting piece. You have to define a loss that you want to minimize. In this case, what it would do is that it would compute a lift and drag ratio, which would be obtained by explicitly just simulating the wind tunnel and then extracting these values, right? And then from this, you would have your objective function, which would compute this lift and drag ratio, right? And which you would then optimize here. And then the magic happens in this line, where you just invoke some automatic differentiation library. In this case, it's AutoGrad. It's an older library, but it's implementing reverse mode automatic differentiation, if I'm not mistaken, on this objective function, which is defined in this way, and in which you will just simulate forward the whole process, right? So that will be a very big and complicated thing, but again, that will be just a big composition of simple primitives, which will then induce a graph of computation, and then on top of which will then be able to run automatic differentiation to obtain gradients, and then plug in this gradient here in a very simple loop where you do gradient ascent on the objective, right? So you just update the parameters, the geometry of the wing, by going because you want to do ascent in the direction, by following the direction of the gradient with steps defined by some learning grade value. Right, then you can run this, and that's the kind of result you would obtain. And I think there are a few videos of the process. Right? And at every step, what you would run is you would simulate the wind tunnel. So we would simulate the dynamics of the air around the object, right? And from this, then you would infer the lift and the drag ratio. Oh, sorry, I just realized I was not using the correct scene. Sorry, so we were not seeing everything. Okay, I hope the explanation was clear anyway. Sorry about that. Right. So let's go back finally to the slides. In this other video, I will not show you, but if you're interested, they are doing more or less the same thing, except that they do it for protein folding. And what is more interesting is that in this case, so they have a simulator of how protein should fold. So that's a very important problem in biology. And so this is something they can simulate forward with classical simulators, except that also what they do is that they parameterize the energy of in this case, what is known as the Boltzmann distribution by a neural network. And then what they want is to optimize the parameters of these energy functions, the parameters of the neural networks, to then, when they are folded, as defined by the simulator, would correspond to a fold which has already been computed using other methods. So this is really nice, and this is more or less like this wing application, except that now you combine both physically motivated simulation with a part which is learnable, which is a neural network. All right, if you're interested in more applications, actually I asked at the beginning of this week on Twitter if people knew about other exciting applications. So many people replied, so I invite you to read this thread. There are many other quite impressive applications of automatic differentiation that go beyond deep learning. And this was really my point also today, to tell you that this kind of algorithm is used beyond deep learning applications. All right, so to summarize, so automatic differentiation is one of the keys, I would say, that enable the deep learning revolution. If you look a few years back, like 10 or 15 years, there were no software library which you could use to automatically derive the gradients. So if you look at older papers, for example, you will find that researchers, they really had some fun in the manual derivation of the gradients. And so you would have pages and pages of appendix with the derivation of these gradients. Of course, now this is not really important any longer because we can automatically compute them and compute them efficiently usually. Then second message for today is that backward mode or reverse mode automatic differentiation is more efficient when the function has more inputs than outputs. That's basically what you should remember, and that's basically what usually is the key in deep learning, because in one place or another, you will connect your neural networks to a loss which is scalar. And so the size of this loss is just one, and given that you have usually millions of parameters, then of course millions is much larger than one, and so the backward mode usually is the best choice when it comes to deep learning. And then, as I've just shown you, applications of automatic differentiation go beyond neural networks. All right, so that's it for today. I didn't expect me to go this long. I'm a bit sorry about that. It was the first time I was giving this lecture, actually. I will try to be quicker next time.